All right, welcome back again, everybody. I was just waiting for a loud car to drive by, like right at the transition point. Um, so welcome back. Today we're going to be doing section 15.2. This is when we're going to extend our double integral to integrals over general regions. So this is where things start to get really fun. Let me pull up the slides and we will get started. Here we go, 15.2. We'll start with some motivation. You might be able to guess the motivation just based off of what I said. We're going to talk about something called the indicator function. This is a pretty simple function that's good to keep in mind. It gets used a lot. I titled this subsection "A Scanner Darkly" because we're going to talk about deciding how you want the integral to scan your regions. The integral is like a scanning machine that's adding things up. Then we will do some double integral examples, and then we'll finish up with properties of double integrals. All right. Okay, so here's the motivation. For single integrals, the domain of integration was always an interval, or it was a union of intervals, right? If you had to like partition it or something like that. But remember that an interval is just a one-dimensional rectangle, and a rectangle is a two-dimensional rectangle, and then a rectangular prism is a three-dimensional rectangle. But anyway, when we had only one variable, there was just an interval, right? And so we only really had two ways to scan the region. We could go from left to right, or we could go from right to left. And that was about it. But in higher dimensions and with multivariable functions, we want to be able to integrate over general regions, not just rectangles, right? So we don't want to be restricted to rectangles. We want to be able to integrate over all sorts of crazy regions, with almost no care about the region itself, if possible. So how are we going to do this? We're going to leverage Fubini's theorem again, because Fubini's theorem is really powerful. It lets you iterate the integration process, but it only works for rectangles. So the way that we leverage this tool is we employ what's called an indicator function. All right. So here's the definition. This is just a broad definition. Don't get bogged down into the details too much. It's really just a function that says, yes, you are on the region, or no, you are not on the region. That's it. So here's the technical definition. Given some subset D of some space X, you could think of X as like the plane or R3, R4, whatever. Pretend you've got a subset of some other set, some space X. Then an indicator function is a function that's defined on the whole space that literally indicates whether or not an element of X is a member of the set D. And here's how it does this. So the indicator function here, it spits out the number 1 if your point is in the set D, or it spits out 0 if your point is not in the set D. That's it. That's how it indicates if you are in the set or not. This is the notation we typically use for the indicator function. It's like a fancy 1, right? The subscript is the region that we are indicating. So this is important to indicate the actual region. X is, I mean, it's a point, it's a number, it's a vector. The whole point here is this is just saying 1 if your point is in D, 0 if your point is not in D. All right, that's what an indicator function is. So how are we going to use this? Well, consider this setup for a minute. Let f be a function of two variables that's defined on a region D. So this region, for example, and we're going to bound this region D with a rectangle R. All right, this is where we're going to get access to Fubini's theorem because we're basically, I really should say, yeah, I'll just leave it at that. We're basically kind of injecting a rectangular interpretation here, but we're doing it in a clever way. We're going to define a new function called capital F, and capital F is our original function little f multiplied by the indicator function for D. Now remember, the indicator function only spits out 1 and 0. So this means that if our point x comma y is in D, this will be equal to 1, and we'll get f of xy. If our point x comma y is not in D, this thing will spit out a 0, which will zero out the entire expression. So then you're just going to have f of x comma y or 0. That's what's happening with this setup. There you go. That's what the indicator function does. It basically lets us indicate whether we want to consider the function on the region D or not. That's the whole setup, okay? So that's what capital F looks like. here's like a three-dimensional look at it. So yeah, what this is going to do is this is going to let us take our construction of the double Riemann integral to general regions because the integrator function will make the integral 0 when the point's not in D. So this is a really good comparison. So this is the graph of f, little f, right? And it's defined on this region D, this little like bean-shaped thing. Well, what does the function capital F look like? Capital F looks like this. It's this little surface in space, and then it's everything outside of the bean, like that. And now what we're going to do is we're actually going to integrate over this rectangle. But we'll see that, on the regions that aren't D, the value of the integral is just going to be 0. But we're going to go through that calculation in a minute. So I will emphasize this a lot, and I do encourage you to think about this like this. So I titled this A Scanner Darkly just because Philip K. Dick is one of my favorite authors, and he's written a lot of he's written a ton of sci-fi stories and novels and everything. And one of his books is called A Scanner Darkly, and so it always makes me think about this when I'm talking about scanning a regions and the fact that some of the region is actually 0, so it's like darkened. Anyway, you can think of the integral as a scanning machine. And in Calc 1, we were just scanning in one direction, maybe the opposite direction. And what we're doing is the integral is adding up all the values of f as you scan from left to right or from right to left. And it's just adding those up. With a double integral, or with multiple integrals in general, doesn't matter how many dimensions you're working in, you have to tell the machine how you want it to scan. Like you have to say, okay, scan this way first, and then scan that way second, and then scan this way third, and then scan this way fourth, and then scan this way fifth. You have to tell the machine how you want it to scan, all right? And that's where the creativity comes in. Um, yeah. So to determine which direction to scan first, it can help if you classify the region just to get an idea of what would be easier. All right. So this is what they call a type 1 region. Um, Full disclosure here, you do not need to memorize type 1 or type 2. I'm not going to quiz you and say like, oh, is this a type 1 region or is this a type 2 region? These are just labels to kind of distinguish between the regions. But here's what a type 1 region looks like. This. So in other words, you could basically, your region is essentially rectangular in one dimension and not rectangular in the other. So it's a region that's defined like this. Y goes between two functions of x, and x goes between two numbers. So let me zoom in on this for just a moment here. There we go. So you see here, this region D, it's basically sandwiched between two functions of x. And then we're going to integrate with respect to x from a to b, right? So it's like between two curves and then between two numbers, two lines, you could even say. This one's also a type 1 region because the same thing. This is like this is the second curve, this is the first curve, and then we could just integrate with respect to x from a to b. So this is what another way a type 1 region can look. And then here's another one. So you might actually have a curve that looks like this and a curve that looks like that. Same deal. We can basically integrate between these two curves, and then we're going to integrate from A to B. So that's in practice how this is going to work. How does it work more rigorously? Well, we need to go back to that indicator function. We need to employ Fubini's theorem, and we're going to skip a lot of those steps in practice, but here we go. So if we want to evaluate an integral of a function f over a region of type 1, we need to choose a rectangle that bounds it. All right, so theoretically, we should be able to find a rectangle that bounds this region. And then really we're going to integrate over that rectangle, but we're not going to integrate little f. We're going to integrate capital F, which is f times our indicator function, right? And what that indicator function will do is it'll zero out the integral here and here. And it will make the integral only pick up on this region right here. But we needed the rectangle so that we could actually apply Fubini's theorem and do this iteratively. So this is what it looks like. And one thing is I'm appealing to a property of integrals that we'll talk about at the end of the slides here, but this is how it looks. So, well, try to follow this. Maybe I'll do it step by step. So if we want to integrate our function little f over our region D, we can instead integrate the function capital F over the rectangle R. And now that we're using a rectangle, we can iteratively integrate by Fubini's theorem. Of course, this has to be continuous, like little f has to be continuous. And so then this would be continuous and yada, yada, yada. All right, now what we're going to do is we're going to break up this integral into three separate integrals using a property of integrals that's called finite additivity. You've seen this before as well in Calc 1 when you had to basically like integrate an absolute value function and you had to break it up into multiple integrals. It's the same thing here. And I'm gonna show you here on the picture now. So there are three separate integrals here. The first integral here is when y goes from c to g1 of x. So that's this right here. This is the region that's indicated by this, because y is going from c to this curve, g1 of x. All right? Then the second integral is the one that's actually going to integrate over d. So it's going to integrate between g1 and g2 right here. So that's what this integral is. And then the third integral is going to be this one, integrating from g2 to d. So that's from here to here. And this is this integral right here. So you see how we're telling it how we want it to scan? We want it to do this, and then this, and then this. Well, because capital F is going to be 0 on this region and this region, we can replace capital F with 0. But the integral of the 0 function is 0, so this completely disappears. This integral is going to be 0. This integral is going to be 0. And then what we're left with is the middle integral, which is the integral that we wanted. So it's the integral of, oh yeah, also want to point out that remember, capital F is equal to little f when you're on D, right? When you're on the region D. And this is exactly what we wanted. So long story short, Fubini's theorem lets us basically integrate the way that we would want to, integrate between two curves and then integrate between two numbers. All right, now I won't go into all of the technical details again, but this is basically how it works. There's also type 2 regions. Type 2 regions are basically the same idea except twisted. It's like rotated to one side. So instead of instead of y being a function, instead of y being bounded between two functions of x, you could have x bounded between two functions of y. Right? So long story short, you integrate between these two curves, and then you integrate y between these two numbers, like so. That's the idea. I say this later on in the slides as well, but which way to integrate is a good question. And that's actually where the creative part comes in, because what you will find is that it is easier to integrate it one way first and then another than it is to integrate it the other way first and then the other. Sorry, I realize that's complicated, but let's try an example. Here we go. So try to do this. Evaluate this integral where D is the region bounded by these two parabolas. And this is one I do want you to try to do on your own. So think about it first. Read this, look at it, think about the question for a moment. Okay, now say something out loud. Remember, it doesn't have to be to anybody. It can be to yourself, to your dog, to your sparkly water, to your keyboard, just whatever. Just say something out loud about what you think you want to do first. Okay, and now try to work it out on your own. Here is my first tip. Try to draw a sketch of the region. So graph these two parabolas and then try to get a picture of what your region looks like. That can help a lot. Okay, now let's do it together. So this is just a parabola with vertex at the origin that's been stretched a bit. This is a parabola that's been shifted up by 1 unit. And so this is what the region looks like in general. There we go. Now, Their points of intersection are right here. How would we find that algebraically? They just intersect when these two things are equal. And then when you solve for x, you get that x is plus or minus 1. And then that will allow you to find the y value of 2 in this case. So how do we describe the region in terms of set builder notation? This is what it looks like. And this is definitely a type 1 region. So here our y values are bounded between two curves that are functions of x. And then x is bounded between two numbers, -1 and 1. So what we're going to do is we want to tell our integral to scan between the two curves first. So literally scanning like this. And then once it is added up, or once it has found the area of all of those slices, we're then going to tell it to scan from -1 to 1 to add up all the areas of those slices. All right? That's the idea. So we're going to integrate with respect to y first, and then integrate with respect to x. So here we go. We're skipping the whole Fubini's theorem part. At this point, we are assuming that the indicator function is saying we are only on our region D, and we're going to jump straight into the iterated integration. Here we go. So now, what's cool about this is our upper and lower bounds are functions of x. So this is why this is so cool. This is so flexible. We're going to integrate this function between these two other functions, between these two curves, right? But everything else is the same. Apply FTC2. Evaluate at the upper and lower bound. Take the difference. See, here we go. Here's FTC2. A little tip, I recommend that you start labeling things with the proper variables. So here, y is going between 1 plus x squared and 2x squared. And then the result should only involve x's, and then we will integrate with respect to x. So once we apply FTC2 here, we get, let me zoom out a bit, we get this. And then we can simplify. So there's like a simplification process, right? But now look, this function only depends on x. So this function is basically, it's the area function. It's the area function for these slices. All right, that's what that is. And then now we're going to add up all of those values. So we're going to integrate now with respect to x. We can use FTC2. X goes between -1 and 1. Simplify, do some arithmetic, and you get 32/15. There you go. Cool stuff. I mean, I think it's cool stuff. All right, let's try another one. So now I want you to try to evaluate this integral over the region D, where D is the region bounded by the line y equals x minus 1, and the parabola y squared equals 2x plus 6. So I do want you to try this one on your own before I do it. So think about it for a minute. Right? And now, what do you think you're going to do first? Say something out loud about what you could do to get started. Okay, now work it out on your own, and we will do it together in just a moment. Okay, here we go. My tip, draw the region first. So get a sketch of the region that will help you decide if you want to treat it as a type 2 region or a type 1 region. Regions can be of multiple types. That's one thing to keep in mind. It could be a type 1 and a type 2 region, which actually is the case in this particular region. So this is what the region looks like. And now we have to make a choice. We have to tell the integral which way we want it to scan first and which way we want it to scan second. And this is a situation where our choice will greatly affect the difficulty of the integration process. So you have to make a wise choice here. So let's take a look at these, and then we'll come back and take a look at what would have happened if we picked the other choice. So looking at this region, thinking about how to scan, I could tell the integral to scan between these curves and then between these numbers, but that seems like it's going to be hard because this curve is actually given by this parabola. This looks like it'll be easier because we could just tell the integral to scan literally from this parabola to this line first, and then just scan from x equals -1 to 4. So in this case, treating it as a type 2 region is going to be easier. So let's do that. Here we go. In this case, we're going to integrate with respect to x first. X goes between those two curves. Here's our function xy. Integrate with respect to x, just apply the good old power rule and use FTC2. Simplify this and you get a function of only y. Remember that at each step of this iteration process, this iterated integration process, you should be losing a variable. So this is only in terms of y. Now treat it as a single variable integral. Integrate with respect to y, apply FTC2, simplify, and you get 36. That's it. So notice this integration process really was not so bad, right? We just had to pretty much just apply the power rule for antiderivatives twice, and it just washed right out. Now, if we had chosen to treat the region like a type 1 instead, it would have been much more difficult. In fact, yeah, see, I have it written out here. If we instead treated it as a type 1 region, we're actually going to have to compute two separate integrals. And the reason is because the bounding curve changes if we try to integrate with respect to y first, right? Yeah. Oh, sorry. Here. This is what I was saying here. If we want to scan vertically first, here's where things get rough. On this region over here, the lower curve is this square root function, and the upper curve is this square root function. But right at this point of intersection, the upper and lower curve, I'm sorry, the lower curve changes. So you see right here, it's like here, this is the lower curve up to this point. Sorry, up to this point. But then beyond this point, this is now the lower curve. So now we have to scan from this line to this square root function. And that's what's being shown right here. Integrate between these two root functions on some interval, and then integrate between the line and the square root function on the other interval. So it's more difficult. It's not impossible. So I won't say that it's not possible, right? But again, this was much easier to do. We didn't have any square roots. We just had to be a little bit, we just had to choose wisely in this case, and it was a good choice to integrate with respect to x first. Okay, all right. Now here's another one that I want you to try, all right? So I'm going to throw up the thinker. Just look at it for a minute. Think about the integral. Right? Now, make a guess at if you want to integrate with respect to y or x first. Say something out loud, right? And now try to work it out on your own. If you find that it is too difficult to integrate with respect to one variable first instead of the other, then just stop, switch the order, but you got to be a little bit careful. So try it out and see what you get. Okay, here we go. All right, so let me see. On the surface, let me see. Yeah, on the surface, looking at this, this is the integral with respect to y going from x to 1. Okay, but sine of y squared, could I anti-differentiate that? And after a moment's thought, maybe trying it a couple of times, you'll realize that none of the techniques seem to work. That's actually because this function doesn't have an elementary antiderivative. So it turns out that trying to integrate with respect to y first here is, yeah, it's not impossible, but you have to basically use a Bessel function to do that first, right? So this is a situation where integrating with respect to y first would be not an optimal choice. I'll just say that. So it would be nice if we could integrate with respect to x first. It'd be nice if we could, like, change the order of integration here. But here's the catch. Remember, a condition of Fubini's theorem was that the region had to be a rectangle. So we can't just willy-nilly change the order of these and just integrate, like, from 0 to 1 and then from x to 1. It's not a rectangle, so that ability to just swap doesn't work anymore. And that's where things get a little bit subtle. If I want to change the order of integration, then what I have to do is I have to tell the integral to scan in a completely different way than it was going to scan in this scenario here. All right? So let's just break things down into something a little more general first, and then let's take a look at the region and then take a look at how we would want to scan it. So like I'll say by uniterating it, we can just write this as a double integral over some region D, and the region D is described like so. So y goes between x and 1, and x goes between 0 and 1, just like that. Now, if we want to change the order of integration, we got to change the way we scan. So let's take a look at the region. This is what the region looks like. Y, yep, yep. This is the line y equals x, y equals 1, x equals 0, x equals 1, y equals x, y equals 1, x equals 0, x equals 1. All right, now, as it is written, we're asking the integral to scan with respect to y first. So it would go from the line y equals x to the line y equals 1. And this we found was actually too difficult. We don't want to scan that way. So what we instead have to do is we want to integrate with respect to x first. With respect to x first. So that means we're going to scan from left to right, from the line x equals 0 to the line x equals y. And then we're going to tell the integral to scan from y equals 0 to y equals 1. So we're scanning left to right first. Then we're going to scan vertically second. Now in this case, the switch was not so bad, and I actually said it out loud. X is going to go from 0 to y. So that will become our new bounds of integration. And then y goes from 0 to 1. So here's what we get. This was our original integral. Now we're going to change the order, but in changing the order, we have to kind of reparameterize the scan. So now notice this is with respect to x, and x goes from 0 to y. And then y is going to go from 0 to 1. Now, because we're integrating with respect to x, this is actually pretty straightforward. We can just use, frankly, it's a version of the power rule, but this is just going to become x sine y squared when we apply FTC2. And remember, x goes from 0 to y, and so now we're left with this. And then what I'm hoping, what I'm hoping is that now when you see this, you should feel a little bit of relief. You should feel like a breath of relief, because this is a function that is, quote, easy to integrate, because you can just use a u sub, right? You can use a substitution. You could even skip the u sub step if you can just see what the antiderivative is, and this is what the antiderivative is. Now we evaluate from y equals 0 to 1, simplify a tiny bit, and we get this. All right, there we go. So this is one of those situations where changing the order was kind of necessary. The idea here is when you do change the order, you've got to re-explain to the integral how to properly scan. It's not going to do it on its own. You got to tell it how to do it. All right, so those excuse me, those are some examples. Now let's finish up with some properties of double integrals. Some of these you've seen before. We've already used a few of them in this section. We're going to use them all the time. These two are very important. Linearity. So this is something that I mentioned in the previous lecture when I was talking about the Rees-Markov-Kakutani representation theorem and linear functionals, right? So this is linearity of the double integral. In essence, if you want to integrate a sum or a difference of functions, you can treat it as the integral, a sum or difference of separate integrals, which is super nice. So you can break apart double integrals over sums and differences. Additionally, you can pull out constant multiples from the integral. So if you want to integrate a constant multiple of a function, you can pull that constant multiple out and just multiply the integral afterward. Only if c is a constant. Only if c is a constant. Then there's this one. So this one is actually what's called monotonicity. And what it says is if f is greater than or equal to g on some region, then the integral of f has to be greater than the integral of g on that region. And then similarly, if the order relationship is reversed, if f is less than or equal to g, then the integral of f is less than or equal to the integral of g. So this is called monotonicity, which makes sense. Basically, if this order relationship is true, then this order relationship is true. It's actually comparable to functions that are increasing or decreasing on an interval. In fact, it is that. It's the same thing. So if you look back at your pre-calculus notes and you talk about what does it mean for a function to be increasing or decreasing, it's basically this. except now our function is the integral itself because it's a function. All right. Then there's this finite additivity. This is the one that we used when we were employing Fubini's theorem to be able to integrate over general regions. And basically it says that if you can write your region D as a union of two other regions, where the two other regions are disjoint except at the boundaries, then you can split the integral up over those regions. So the integral of f over the region D can be written as a sum of two integrals, 1 over d1 and 1 over d2. Here's a picture of it. So here's the region D. But what we could do is we could slice D right here, and then integrating over D is the same as integrating over D1 and then D2. Why is this helpful? This is helpful because this type of split may let you redefine the region in terms of a type 1 region or a type 2 region. So here, it's neither type 1 nor type 2 because there's this kind of like wacky curve here. So it's not type 1 or type 2. But if you slice it cleverly, then what you get is a type 1 region, right? So now here y is bounded between two curves with respect to x. And then this is a type 2 region. So x is bounded between two curves with respect to y. Now we can now we can integrate piecewise. That's what we're doing here. All right. Then we've got an area formula. This is always a good one to remember. This formula actually generalizes, and I'm hoping that some of you saw the one-dimensional version of this in Calc 1 or Calc 2. If you integrate the unit function, then it just gives you the area of the region, so the area of D. This makes sense if you think about it intuitively. Remember, dA is like the change in the area. So if I add up all the change in area over a region D, then I'm going to get the area of the region D. That's what it is. For single variable functions, it actually gives you the length of the interval. So if this were a single integral, like a single integral over some interval from a to b, and you integrated the unit function, this is the same thing as integrating over a to b dx. This will actually just give you the length of a. Oh, sorry, I'll just say. It'll give you the length of the interval. So maybe I'll say the length of b comma a. Oh my gosh. A comma b, which is just b minus a. And that actually generalizes further. So we're going to see when we talk about triple integrals and multiple integrals, yeah, if you did a triple integral of the unit function, it's going to give you the volume of the region. If you did a quadruple integral of the unit function, it's going to give you the hypervolume of that hyperregion. So all that stuff is very naturally generalizable, or this one is. And then the last property we have is called boundedness. So if our function f is bounded below and above, then our integral, the integral of f, is also bounded below and above. And it is bounded below and above by exactly the minimum of f times the area of D and the maximum of f times the area of D. And that's basically it. So our function is trapped. So remember, these are basically like surfaces, right? There's surfaces in space. And if you know that there's a maximum value and there's a minimum value, then whatever that integral is, it's got to be between the volume of these boxes. That's what it's saying. All right. On that note, let's play. So I like this one. It's a little bit short, but there's a lot of really important content in here. Just remember that when you change the order of integration, if it's not a rectangle, you have to tell the integral how to scan all over again. You got to tell it how to scan, and you got to think about how you want it to scan, all right? It's just a machine. It will not know what you mean if you do not tell it how to do it. But that's my last tip for this section, all right? Thank you all again for watching, and I'll see you next time.